In the spring of 1944, the Pacific Ocean stretched calm and deceptive under a pale morning haze. Among the endless waves, an American destroyer of the Fletcher class maintained a lonely patrol near the Solomon Islands, a region that had once been the center of fierce fighting and was now a maze of reefs, wrecks, and drifting debris from past battles. The crew had grown used to routine vigilance, scanning the horizon for silhouettes, monitoring the radar screen for fleeting echoes, and listening to the deep, rhythmic heartbeat of the ship's engines that kept them alive far from any shore. The war seemed distant for a brief moment, but in the Pacific, peace never lasted long. Shortly after noon, the destroyer's radar picked up a formation of fast-moving aircraft coming from the northwest. It was a squadron of Japanese dive bombers, most likely D-3A, VAL, planes operating from one of the remaining island airfields in the region. They had spotted the destroyer and descended swiftly, the sunlight flashing off their wings as they dove out of the clouds. The ship's anti-aircraft guns opened fire, tracing arcs of orange through the sky. The air filled with the noise of explosions and the metallic thud of shrapnel striking steel. One bomb fell dangerously close to the port side, detonating just below the waterline. The explosion did not pierce the hull but delivered a violent shockwave that tore through the machinery spaces. Pipes burst, valves cracked, and the starboard turbine shuddered as its bearings seized. The engine room filled with steam and the smell of burned oil. The destroyer's vibration changed instantly. The deep, steady hum broke into uneven jolts, then silence. The main engine had failed. For a few seconds, the ship drifted helplessly, her bow swinging off course under the pressure of the wind and current. The officers on the bridge felt the sudden loss of power ripple through the entire vessel like the stopping of a heart. The crew scrambled to contain the damage. Pumps began clearing the flooded compartments, while damage control teams sealed off ruptured lines. The chief engineer reported that the port turbine could still function, but the starboard unit was completely immobilized. Without it, the ship's maneuvering power was halved. In combat, that meant death. The destroyer could still move, but too slowly to evade another attack. Above, the anti-aircraft gunners scanned the sky, expecting a second wave. Below, in the depths of the ship, a different kind of battle began, the struggle to make the machinery live again. John Miller, the ship's senior machinist's mate, descended into the engine room through a narrow steel ladder slick with condensation. He had spent years at sea and had seen engines fail in every possible way, but this damage was unlike anything he had encountered. The turbine casing was cracked, and one of the reduction gears had jammed. The vibration from the explosion had misaligned the shaft, throwing the whole system out of balance. A few inches to the side and the bomb would have ripped through the hull. Now it had left them crippled but afloat. Miller studied the damage silently, his hands tracing the edges of the broken metal. He knew the destroyer's fate now depended not on the guns or the radar, but on the quiet precision of men working in the heat and dark. The ship drifted several miles off its patrol course, maintaining radio silence to avoid detection. The tropical air was thick with humidity, and every deck plate radiated heat from the boilers. Engineers improvised temporary fixes, patching ruptured pipes with clamps and rope. Yet the main engine remained dead, an inert mass of steel that refused to respond. The nearest repair base was on Tulagi, more than 80 nautical miles away. Without propulsion, the destroyer risked drifting into enemy-controlled waters or onto one of the countless coral reefs that dotted the area. Above deck, the horizon glowed red as the sun began to sink behind the islands. The faint smell of burning oil still lingered in the air. The officers debated their options, weighing the risks of waiting for assistance against the danger of being discovered at dawn. In the engine room, Miller remained at his post, reviewing blueprints from memory. He understood the machinery better than anyone else aboard. Every vibration, every sound was familiar to him. And now that silence felt unbearable. If the turbine could not be restarted, the destroyer would have to be abandoned. The thought was unthinkable. In the flickering light of the emergency lamps, Miller examined the damaged components again. The gear assembly was beyond repair with the tools they had, and the replacement parts stored on board were either worn out or incompatible. Yet he knew that somewhere nearby, beneath the waves, lay the remains of American transports sunk during the early battles for the Solomons. Those wrecks, stripped by time and coral, still contained machinery, pumps, and fittings that might be adapted. The sea had claimed them, but it had also preserved them. To most sailors, they were forgotten debris. To a mechanic, they were a lifeline waiting to be reclaimed. By nightfall, the Pacific had gone quiet again. The wind dropped, and the surface turned mirror smooth. The destroyer floated motionless, her hull scarred but intact, her crew waiting in tense uncertainty. The only sound came from the distant hiss of the boilers still generating minimal power for lights and pumps. Down below, surrounded by the echo of dripping water and the smell of metal and salt, John Miller began forming a plan. He understood that no rescue would come soon enough. The ship's survival now depended on his hands, his memory, and whatever the sea was willing to give back. The inspection revealed the full extent of the damage only after the noise and chaos had subsided. The blast that struck near the port side had not torn open the hull, but it had sent a shockwave through the machinery compartments powerful enough to warp steel. The engineers worked in sweltering heat, their flashlights cutting through the haze of steam that still clung to the walls. When they removed the access plates to the starboard turbine assembly, they saw the cause of the failure. The main shaft bearings had seized, their housings cracked from the impact. One of the reduction gear bushings had split cleanly along its outer edge, leaving a jagged seam where oil now leaked and dripped into the bilge. It was a kind of damage that could cripple even a well-supplied repair ship, let alone a destroyer adrift far from any base. Miller and his team began cataloging what was left intact. The boiler pressure was holding steady, and the auxiliary pumps were still operational. But without the primary turbine, the destroyer's power train was effectively broken in half. The port turbine could provide limited thrust, yet the imbalance of torque would make the ship almost impossible to steer for long. The shaft alignment had shifted by several millimeters, and the slightest vibration could cause further structural fatigue. On a destroyer that depended on high-speed maneuverability to survive, this kind of limitation was a death sentence. When Miller checked the spare parts inventory, his fears were confirmed. The war had stretched logistics to the limit, and most ships carried only minimal reserves of critical components. The naval bases at Espiritu Santo and Tulagi had absorbed every available turbine bearing and gearbox part months earlier, diverting them to major overhaul projects. Even the repair ships in the area were running low on precision parts. The destroyer's onboard machine shop was equipped for small tasks, fabricating brackets, valves, and connectors, but not for crafting the kind of high-tolerance components a turbine demanded. The chief engineer tried to raise headquarters by radio, but the communication circuits were unstable. The antenna array had been partially damaged during the air attack, and only short-range transmissions were possible. Static drowned out most of the outgoing signals. The limited contact they managed to establish brought little comfort. The nearest fleet tug capable of towing them to safety was more than 100 miles away, and enemy aircraft still patrolled the area between. The Pacific in 1944 was vast, and even a single day of delay could mean disaster. The ship carried enough fuel and food to last, but every hour without propulsion brought them closer to drifting into hostile waters. As the engineers gathered in the lower engine room, the temperature climbed to unbearable levels. Condensation dripped from the pipes overhead. The noise of auxiliary machinery filled the confined space, masking the low groan of metal under strain. They discussed every possible workaround, running on one shaft, coupling the port turbine to the auxiliary generator, even using the ship's pumps to create artificial thrust, but none were feasible. The destroyer's design left little margin for improvisation. Its power plant was a masterpiece of precision engineering, but it was also unforgiving. One cracked bearing could immobilize the entire propulsion line. Miller understood this better than anyone. He had served in the Navy's engineering course since before the war and had spent countless hours inside the narrow spaces of turbine rooms, learning how each system responded to pressure, heat, and time. He knew that the only way to restore the engine was to replace the broken bearing assembly entirely. But where could he find a part like that, 200 miles from the nearest foundry? He remembered the stories told among the engineers stationed in the Solomons. In the early months of the campaign, dozens of American transports and auxiliary ships had been sunk during supply runs to Guadalcanal. Many of those wrecks still rested in shallow water, their cargo holds and machine rooms relatively intact. Over the past year, divers and salvage crews had occasionally recovered valuable equipment, valves, motors, sections of piping, from them. If he could reach one of those hulks, there was a chance he could find components close enough in size to adapt for temporary use. The idea was dangerous and desperate. The waters around the Solomon Islands were unpredictable, filled with strong currents and debris. Many wrecks lay near enemy-controlled shores. Yet, from an engineer's point of view, it was a rational risk. The destroyer's crew could not remain adrift for long. The tropical heat would soon exhaust the cooling systems, and bacterial growth in the water tanks would become a secondary threat. Without movement, the ship's hull would also begin to accumulate marine growth that could damage the intake valves. By late evening, the engineers had exhausted every on-board option. The chief engineer ordered the surviving turbines sealed off to prevent further contamination, and the auxiliary systems were switched to minimal power. The destroyer's speed was reduced to a crawl. Every man in the engine room knew the truth. They did not dare speak aloud. They could not reach Tulagi like this. For John Miller, the situation had crossed the line between repair and survival. The manuals and procedures that defined his work no longer applied. This was not a question of following naval protocol. It was about keeping the ship alive through ingenuity. As he looked over the warp-bearing housing one last time, he recognized the shape of his challenge, not mechanical, but human. Somewhere beneath those waters lay the remnants of other American ships, relics of earlier battles, stripped by time but still holding what he needed. The destroyer's only hope now rested on the possibility that one man's understanding of metal and motion could bridge the gap between ruin and survival. By 1944, the engineering culture of the United States Navy in the Pacific had evolved into something far removed from the rigid textbook procedures that had guided peacetime operations. The vast distances, tropical climate, and constant combat had forced engineers, machinists, and shipfitters to become improvisers of the highest order. The war in the Pacific was fought not only with guns and aircraft but with tools, welding torches, and the ingenuity of men who had learned to repair the unrepairable. Every harbor and island base between Australia and Hawaii had become a kind of floating workshop, where the line between battlefield and machine shop had blurred completely. The early months of the Guadalcanal campaign in 1942 had revealed a harsh truth. The U.S. Navy was fighting a war thousands of miles from its industrial heartland. Ships damaged in combat could not always be towed back to the great naval yards in San Francisco or Pearl Harbor. The Solomons, New Hebrides, and other island chains became improvised repair centers, where naval engineers had to make do with whatever could be salvaged. They often used the remains of ships and aircraft destroyed in earlier battles as a source of spare parts. The practice was known among crews as cannibalization, a word that captured both its desperation and its creativity. On islands like Tulagi, Espiritu Santo, and Guadalcanal itself, the Navy's service squadrons, known as Cerveron 4 and later Cerveron 10, set up what were effectively floating industrial cities. Repair ships, foundries, and machine barges formed the backbone of these mobile depots. They could rebuild boilers, fabricate new propeller shafts, and even weld hull plates underwater. But their resources were limited, and the flow of supplies from the United States often lagged behind the pace of battle. When a destroyer, transport, or landing craft limped into anchorage, the first question the engineers asked was not, "What do you need?" but, "What can we take from what's already here?" The Liberty ships, mass-produced cargo vessels that carried everything from food to fuel, became a vital source of raw material when they were damaged or lost. Their engines, valves, and pumps were simple and standardized, which made them perfect donors for makeshift repairs. Engineers scavenged piston rods, bearings, and even hull plating from partially sunk Liberties, hauling them ashore or cutting them loose from shallow wrecks. In some cases, damaged aircraft served a similar purpose. The aluminum skins of down B-24s and PBY Catalinas were cut apart, and used to patch ship bulkheads or build ventilation ducts. What had once been symbols of destruction became the raw material of endurance. The tropical climate added its own challenges. Saltwater corrosion and heat worked against every system on board a ship. Turbines and boilers suffered from rapid metal fatigue, lubricants broke down, and cooling systems clogged with sediment and marine growth. Supply ships often carried limited quantities of high-grade steel and precision bearings, which meant that engineering crews had to repurpose whatever they could. The Navy began to formalize this improvisation under the concept of Field Expedient Repair, encouraging engineers to adapt civilian methods, use local materials, and report successful innovations back to the fleet. By mid-1944, Espiritu Santo had become the largest advanced base in the South Pacific, home to repair docks capable of handling everything from destroyers to aircraft carriers. It was a place where shipwrights, machinists, and divers worked around the clock, patching hulls with salvaged armor plate, reconstructing engines from mismatched components, and keeping the Pacific Fleet alive. Many of the mechanics stationed there had no prior naval background. They were factory workers, auto mechanics, and engineers drafted from civilian life who brought a practical, problem-solving mentality to military repair work. Their adaptability became a defining feature of American engineering in the Pacific theater. The Navy also created floating repair units, ships like USS Vestal and USS Prometheus, that followed the fleet and provided emergency assistance wherever it was needed. These vessels carried their own workshops, lathes, and portable foundries, allowing them to cast replacement parts on site. But even these specialized ships could not meet the endless demand. When frontline vessels like destroyers or patrol boats suffered mechanical damage in remote waters, they had to rely on their own engineering crews to improvise solutions. This decentralized, inventive approach to maintenance gave the U.S. Navy a crucial advantage. Japanese forces, bound by stricter command structures and limited industrial support, could rarely restore damaged ships so far from home. American crews, by contrast, turned the act of repair into a tactical skill. They learned to see every broken ship, every wreck, as a potential resource. It was a mindset born of necessity and refined through experience. For men like John Miller, this environment was both a challenge and a proving ground. Aboard destroyers, the machine spaces were small, hot, and dangerous, yet they were also places of invention. The engineers who worked there were not just maintainers, they were builders, experimenters, and survivors. They inherited the lessons of Tulagi and Espiritu Santo, where the first makeshift repairs had kept the fleet moving when the outcome of the war was still uncertain. By 1944, those lessons had become doctrine. Cannibalization was no longer a last resort. It was an accepted part of the Navy's logistical system. In this context, what Miller planned to do was not reckless. It was the natural extension of an engineering culture shaped by war. He was part of a generation of mechanics who understood that machines could be rebuilt from fragments, that the sea itself was full of resources waiting to be reclaimed. The Navy's ability to adapt, to improvise, and to repurpose was as decisive a weapon as any bomb or torpedo. The story of his destroyer was not an anomaly but a reflection of the greater truth of the Pacific War. Survival depended not only on firepower, but on the quiet, relentless ingenuity of those who refused to let a machine die. Night fell over the Solomon Sea like a curtain, turning the surface into a sheet of ink broken only by the faint shimmer of phosphorescence. The destroyer drifted silently under low power, her lights dimmed to avoid detection. The air was heavy with humidity, carrying the smell of fuel and salt. Somewhere beyond the dark horizon lay the skeletal remains of the SS Seminole, an American transport that had gone down during a Japanese air raid in November 1942. Her wreck had become a landmark to the few sailors who still remembered the first desperate months of the Guadalcanal campaign. For John Miller, that wreck was not a relic of loss, it was a chance at survival. According to the ship's logs preserved at the forward base, the Seminole had been hit while unloading supplies off Lunga Point. She had burned for hours before sinking in shallow water near the coast, where the seabed was littered with the debris of both American and Japanese ships. Divers from the Navy's salvage teams had stripped her of anything immediately useful months earlier: guns, anchors, and copper wiring, but they had not bothered with the inner machinery. The main engine room, sealed under silt and rust, still held the bones of a once living ship. That was where Miller hoped to find what his destroyer needed most: bearings, bushings, and pipe fittings that could be adapted for a crippled turbine. Just after midnight, under a moon veiled by thin clouds, Miller assembled a small group of volunteers, 2 machinist's mates and a boatswain's assistant who had some experience with diving gear. The destroyer's captain authorized the mission reluctantly, knowing it would take them close to enemy-patrolled waters. A motor launch was lowered quietly into the sea, its engine muffled with canvas to reduce the noise. The men carried basic salvage tools, hand wrenches, pry bars, and an old Mark V diving rig, the same type used by Navy salvage divers since the 1930s. It was heavy, awkward equipment, but it could withstand the shallow depths where the Seminole lay. The journey to the wreck took less than an hour. The sea was calm, but every wave carried the sound of distant thunder from storms over the horizon. When they reached the site, they could see the faint outline of twisted metal beneath the surface, illuminated occasionally by their flashlights. The Seminole's hull rose from the seafloor like the ribs of a dead leviathan, its upper decks collapsed and colonized by coral. Small fish darted through portholes, their silver scales catching the light like sparks. For a moment, the men could almost forget that this graveyard of ships had once been a battlefield. Miller went down first. The water was warm and murky, the visibility barely a few meters. The beam of his flashlight cut through the darkness, revealing the tilted machinery spaces. The Seminole's engine room was surprisingly intact. The great diesel engines lay on their sides, overgrown with barnacles but still recognizable. He brushed away the sediment from a set of bronze bushings near the base of one of the shafts. The metal, protected from full exposure to seawater, had resisted corrosion better than expected. It was not perfect, but it could be remachined and pressed into service. One by one, the divers brought the pieces to the surface: heavy rings of bronze and steel, fragments of broken pipe, a section of flange that matched almost exactly the size Miller had measured earlier in the destroyer's engine room. They worked slowly, surfacing at intervals to rest and coordinate their next descent. Each trip carried risk. The currents near the wreck were unpredictable, and more than once they had to cut loose tangled lines or fight against the suction of the silt that clung to the machinery. Yet they pressed on, driven by the knowledge that the ship waiting beyond the horizon could not survive another day without those parts. By the time the eastern sky began to pale, their small boat was piled with the spoils of their salvage: 6 bronze bushings, 2 sections of hydraulic tubing, and a heavy gear housing that they had cut free from its rusted bolts. Every piece was covered in algae and barnacles, but to Miller's trained eye, it looked like gold. They hoisted the load aboard and turned back toward the destroyer, the boat straining under the extra weight. Behind them, the Seminole lay in silence once more, giving up one final contribution to the war she had not survived. When they reached the destroyer, the crew helped lift the salvaged metal onto the deck with block and tackle. The men were exhausted, their hands raw from salt and metal, but there was no time to rest. The engineers began cleaning the parts immediately, scraping off the corrosion with chisels and wire brushes. The bronze pieces were soaked in diesel oil to dislodge the remaining silt. The air filled with the smell of burnt fuel and wet metal. Down in the engine room, Miller inspected each salvaged part in turn, comparing dimensions with calipers and measuring rods. Some pieces would need to be filed down, others would require makeshift spacers to fit the destroyer's assembly. None of it matched perfectly, but the tolerances were close enough for him to believe it could work. He knew they could not rebuild the turbine to factory standards. What he aimed for was something more basic, to make it live long enough to move. The men worked without blueprints, relying on instinct and experience. They used torches and hand drills, aligning each part by sight and feel. The destroyer's small machine shop came alive again, its tools clattering through the night. Sparks flew as steel met bronze, and the sound of hammering echoed through the ship. There was no certainty, no guarantee of success, only the rhythm of labor and the faint hope that the pieces they had taken from the sea could once again drive a ship through it. As dawn rose over the Pacific, the deck glowed with the dull sheen of polished metal. What had been retrieved from the grave of the SS Seminole was now laid out in neat rows, ready to be fitted into the heart of another vessel. For a brief moment, the war paused. 2 generations of ships, one dead, one barely alive, were connected by the hands of the men who refused to let either be forgotten. It was not heroism that drove them, but something quieter and stronger, the conviction that no machine, however broken, was truly beyond repair as long as human will remain to rebuild it. The work began in the lowest part of the destroyer, where heat and noise mixed with the smell of oil and metal. The salvaged parts from the SS Seminole were brought below deck one by one, their rough surfaces cleaned and examined under the dim yellow glow of portable lamps. John Miller moved methodically, his mind tracing the layout of the turbine assembly he had memorized through years of service. The starboard engine lay silent and half dismantled, its bearings seized, its casing cracked by the concussion of the near miss. Around him, every sound carried weight: the slow hiss of steam from pressure lines, the clang of wrenches on steel, the muffled hum of the auxiliary generator that kept the lights alive. The first task was to remove the shattered bearing that had locked the turbine shaft. It was fused to its housing by heat and impact, the metal warped and brittle. Miller and his crew used a combination of chisels, torches, and hammers to free it, working in shifts to avoid exhaustion. The confined space made every movement deliberate. There was barely enough room for 2 men to stand upright. When the bearing finally broke loose, it fell to the deck with a heavy thud that echoed through the hull. What remained was a jagged cavity in the heart of the propulsion system, a void that had to be filled with something that would not fail under the immense stress of rotation and heat. From the pile of salvaged parts, Miller selected a bronze bushing from an auxiliary pump recovered from the Seminole. It was nearly the same diameter as the destroyed bearing, but a few millimeters too wide. In a normal shipyard, the piece would have been machined to exact tolerance on a precision lathe. Here, on a drifting destroyer in wartime seas, they had to rely on hand tools and intuition. Miller wrapped the bushing in sandpaper and spent hours grinding it down manually, stopping frequently to measure the fit against the shaft. The work was slow, punishing, and precise. By the time it seated properly, his hands were raw and streaked with metal dust. Once the new bearing was in place, the question of lubrication became critical. The explosion had destroyed part of the oil distribution manifold, leaving the turbine without a reliable pressure feed. Miller improvised a replacement from the ship's hydraulic steering system. Using copper tubing stripped from the old rudder assembly, he routed a new oil line around the damaged section, securing it with clamps and reinforced gaskets made from cut sections of rubber hose. The flow control valve was taken from a decommissioned bilge pump, its pressure settings adjusted manually. It was a crude solution, but it would ensure that oil reached the moving parts during startup, reducing the risk of another seizure. The cracked casing of the reduction gear presented a different problem. Without reinforcement, the vibration of the turbine could cause it to fracture completely, tearing the system apart. The mechanics scavenged steel plates from a damaged bulkhead near the aft section of the ship. They cut the plates into narrow strips with an oxyacetylene torch and bolted them across the fracture lines like surgical stitches. Each joint was sealed with molten solder and reinforced with weld beads laid down by a portable arc welder powered by the emergency generator. The generator sputtered intermittently, forcing them to pause while the electricians coaxed it back to life. The flickering lights above their heads mirrored the uncertainty of their task, but they kept working, hour after hour. The heat in the engine room became suffocating. Condensation streamed down the walls, and the air was thick with the acrid scent of burning insulation. The men worked in silence, communicating through gestures and nods. Sweat dripped from their faces onto the metal surfaces, mixing with oil. Every adjustment carried a risk. A misaligned shaft could shear itself apart on ignition, and an unstable weld could burst under load. Yet Miller trusted his senses: the faint resistance of the wrench, the tone of a tightening bolt, the subtle vibration that signaled balance. It was the kind of judgment that no manual could teach, born of experience and necessity. When the assembly was finally complete, the engineers began the alignment checks. Using chalk marks and measuring rods, they verified that the turbine and gearbox were properly centered along the shaft axis. The bronze bushing turned smoothly under manual rotation, its surface glistening with a thin film of oil. The reinforced casing held firm, the welds cooling to a dark, even sheen. Miller ordered the system purged with compressed air to remove any debris, and then he connected the temporary oil lines to the auxiliary pump, watching as the pressure gauge began to climb. By the second night, fatigue had set in across the team. Eyes bloodshot and hands trembling, they moved as if guided by instinct alone. The destroyer's engines had not run in nearly 3 days, and the crew above deck waited in anxious silence. Just before dawn, Miller gave the order to begin the startup procedure. The boiler pressure was raised slowly, steam hissing through the feed lines toward the turbine compartment. The ship seemed to hold its breath. When Miller opened the main valve, the turbine emitted a low groan that rose into a steady hum. The bronze bearing held firm, spinning in perfect rhythm. The vibration that had once shaken the entire hull was gone. For a moment, the sound of machinery replaced the fear that had haunted every man aboard. The ship began to move again, slowly at first, then with growing confidence. The improvised repair had worked. What Miller and his team had accomplished in less than 48 hours would have taken days in a proper dockyard. They had rebuilt a crippled engine with parts salvaged from a shipwreck, welding, grinding, and shaping by hand in the sweltering dark. It was not perfection, it was survival engineered from fragments. The destroyer's turbines turned once more, driving her bow through the waves towards safety. In that moment, the boundary between machine and man disappeared. The ship lived because they refused to let it die. When the destroyer finally regained power, her first movements were cautious, almost hesitant. The starboard turbine, rebuilt from salvaged bronze and steel, began to turn with a deep mechanical rhythm that reverberated through the ship's hull. The sound was uneven at first, a series of rising and falling notes, as the newly fitted parts adjusted to heat and pressure. But after a few minutes, the vibration stabilized, and the engineers could feel the ship's pulse return. For the first time in days, the vessel was no longer adrift. Her bow pointed southeast, toward the Allied anchorage at Tulagi, more than 80 nautical miles away. It was a long distance for a crippled ship, but now there was movement, and that was enough. The officers ordered a slow and steady speed, no more than 10 knots, to avoid overloading the improvised bearing. The sea was calm, but the crew moved with quiet tension, knowing that any imbalance in the turbine could end their progress in an instant. The engineers remained in the machine spaces, monitoring the oil pressure and temperature gauges without pause. Every hour, Miller checked the bronze bushing for signs of overheating, his fingers hovering over the casing to feel for vibration. The patched oil lines held, though one joint began to leak slightly, forcing a temporary patch with layers of canvas and sealant. Nothing about the system was elegant, but it worked, and that was all that mattered. The destroyer moved through waters once known as Iron Bottom Sound, the graveyard of ships sunk during the first fierce months of the Guadalcanal campaign. The crew could see the glint of sunlight reflecting from wreckage below the surface, American, Japanese, and Australian ships resting together on the seafloor. It was fitting, Miller thought, that their own survival now depended on a ship that had gone down here 2 years before. The Seminole, in her ruin, had given them a second life. By late afternoon, the coast of Tulagi came into view, a narrow strip of green rising from the blue horizon. The small island had served as a critical Allied base since 1943, its harbor crowded with supply ships, repair tenders, and floating workshops. As the destroyer approached, smoke rose from the stacks of the service squadron anchored offshore. When they signaled their arrival, the harbor master responded with disbelief. No one had expected the ship to make it back under her own power. A tug was dispatched to escort her through the channel, but she entered the anchorage unaided, her engines turning just enough to guide her toward the repair dock. Once moored, the engineering teams from the shore-based maintenance unit boarded immediately. These men were veterans of countless emergency repairs. They had seen ships patched with concrete, boilers sealed with clay, and propellers replaced by mismatched blades. Yet what they found aboard the destroyer astonished even them. The improvised bronze bushing, cut by hand and fitted without a lathe, had withstood nearly a full day of continuous operation. The welded reinforcements on the reduction casing showed no signs of failure. The oil system, though assembled from hydraulic lines and spare valves, had maintained consistent pressure throughout the voyage. It was a triumph of improvisation and endurance. The senior naval engineer on Tulagi ordered a full technical inspection, documenting every detail of the repair. The report described the procedure as a field adaptation of available materials under combat conditions, noting its effectiveness despite the lack of standard tools or replacement parts. The phrase, self-sufficient repair in isolation, appeared in the summary, a term that would later enter the Navy's lexicon for describing instances of exceptional field engineering. Miller's name appeared not as a hero, but as a craftsman whose technical intuition had turned disaster into survival. For the next several weeks, the destroyer underwent a formal overhaul. The temporary parts were replaced with factory-standard components shipped from Espiritu Santo, and the turbine was restored to full capacity. Yet even as new steel replaced the salvaged bronze, the memory of the voyage remained vivid among the crew. The men spoke of how the ship had seemed to come alive again, how each pulse of the engine had felt like a heartbeat echoing through the hull. The engineering officers on Tulagi sent copies of the repair report to the Fleet Maintenance Command at Espiritu Santo, where it caught the attention of instructors at the Naval Machinist School. They saw in Miller's solution a perfect case study for teaching adaptability. Excerpts from the report were later included in a technical manual titled Field Repairs and Improvised Fabrication in Forward Areas, distributed throughout the Pacific Fleet in 1945. It emphasized the value of resourcefulness, urging young engineers to trust their knowledge of materials as much as their equipment. The story of the repair circulated quietly within the fleet, passed from one engineering crew to another. It was not told as a tale of glory but as a lesson in persistence, the understanding that a ship could survive not through perfect design, but through the determination of the men who kept her alive. For John Miller and his team, the greatest reward came not in medals or recognition, but in the simple fact that their ship had made it home under her own power. The story of the destroyer's repair began to spread quietly through the channels of the Pacific Fleet long before the war ended. Within weeks of the ship's arrival at Tulagi, copies of the engineering report had circulated among the service squadrons stationed across the South Pacific. It was discussed in mess halls and machine shops from Espiritu Santo to Manus, not as an act of heroism, but as a demonstration of what could be achieved when experience and necessity converged. The destroyer's recovery became one of many case studies that illustrated how improvisation had become as vital to naval warfare as gunnery or navigation. By 1944, the United States Navy was maintaining the largest mechanical force ever assembled at sea. Thousands of ships, destroyers, transports, landing craft, and auxiliaries operated far beyond the reach of mainland shipyards. The logistical chain stretched across 12,000 miles, and every link was vulnerable to weather, enemy action, or simple mechanical failure. In this environment, the traditional model of centralized maintenance had broken down. Repair ships, floating dry docks, and forward bases had to become self-sufficient, often rebuilding complex machinery with salvaged material and hand tools. The Navy began to formalize these methods under a growing body of technical doctrine known as Field Expedient Repairs. This term appeared officially in reports issued by Service Squadron 10, the massive mobile support unit that followed the fleet across the Pacific. It referred to any repair conducted under combat or isolated conditions using non-standard materials or procedures. The destroyer's case, along with others like it, provided concrete examples of how critical systems could be restored without factory equipment. Engineers who reviewed the Tulagi report praised its clarity and ingenuity. The Navy's Bureau of Ships later cited it as evidence of the importance of training sailors not merely as technicians, but as problem solvers. At Espiritu Santo, the largest rear area repair base in the South Pacific, instructors at the machinist and engineering schools began to incorporate such stories into their teaching materials. They used them to illustrate the principle that the effectiveness of a repair did not depend solely on precision, but on understanding the mechanical logic of a system. The example of Miller's team showed that even a turbine, a component once thought too delicate for field modification, could be revived with careful craftsmanship and the intelligent use of scavenged parts. This became a cornerstone of post-war engineering philosophy within the Navy, the emphasis on adaptability and empirical judgment over rigid adherence to procedure. The influence of this approach went beyond individual ships. Entire service squadrons began to stockpile damaged or outdated components specifically for reuse. Bearings, valves, and turbine parts from decommissioned vessels were stored in salvage pools at forward bases, ready to be repurposed when needed. The Navy established dedicated salvage and repair units whose sole mission was to retrieve usable material from wrecks and damaged ships, both Allied and enemy. This practice of secondary utilization conserved enormous quantities of metal and reduced dependency on long supply lines from the mainland. When the war moved north toward the Philippines and Okinawa, the doctrine of field repairs proved indispensable. In those campaigns, destroyers and landing craft were struck daily by kamikaze attacks and artillery fire. Without immediate access to dry docks, their survival often depended on shipboard engineers performing the same kind of improvisations that had once saved Miller's vessel. Crews fashioned replacement bulkheads from steel plating torn off damaged ships, created fuel line couplings from salvaged aircraft parts, and welded patch plates underwater while under enemy fire. These acts, repeated countless times, kept the Pacific Fleet operational through the final year of the war. After the war, as the Navy began to analyze its vast technical experience, many of these improvisations were codified in training manuals and engineering bulletins. The Bureau of Ships published a compilation titled Field Expedient Repairs, Lessons from the Pacific, which summarized hundreds of examples of successful emergency maintenance. The section dealing with turbine and propulsion systems referenced several cases originating from the Solomon Islands theater, including one that mirrored Miller's repair in both method and result. These documents were later used to design post-war curricula for naval engineering officers, emphasizing creativity under pressure and the practical value of mechanical intuition. The philosophy that emerged from these experiences endured long after 1945. During the Korean War and later conflicts, Navy engineers continued to apply the lessons of field adaptability, treating broken machinery not as a failure, but as an opportunity for invention. The culture of self-reliance that had taken root in the Pacific became part of the Navy's institutional identity. Historically, the practice of repurposing components and performing ad hoc repairs is well documented in U.S. naval archives. Service Squadron 10's reports from 1944 to 1945 mention multiple instances of destroyers and auxiliary vessels completing long transits using temporary bearing assemblies, welded hull patches, or improvised oil systems. Tulagi and Espiritu Santo served as central hubs for these innovations, where fleet engineers shared blueprints and technical reports. The destroyer's repair, though one of many, reflected a broader truth about the Pacific War, that victory depended not only on industrial power, but on the creativity of men who refused to let steel dictate the limits of survival. When the war ended in 1945, John Miller returned to the United States along with thousands of other sailors who had spent years scattered across the Pacific. His ship was eventually decommissioned and sent to a reserve fleet, but his work as a machinist's mate had left a mark far beyond its hull. Like many of the Navy's wartime engineers, he carried home not just the memories of battle but the lessons of survival through invention. The Navy, recognizing the extraordinary value of that experience, began inviting seasoned technical personnel to serve as instructors in its post-war training programs. Miller was among those chosen. He was assigned to the Naval Engineering School in Norfolk, Virginia, one of the largest technical education centers in the country, where the next generation of mechanics and shipfitters would learn the craft of keeping a fleet alive. The atmosphere in Norfolk during those years reflected both relief and transformation. The war had accelerated every branch of engineering, and the Navy was determined to preserve the practical knowledge that had emerged from the chaos of the Pacific. Instruction manuals were rewritten to include case studies of field improvisation, diagrams of makeshift oil systems, and repair procedures performed under combat conditions. In classrooms filled with young sailors fresh from civilian life, instructors like Miller bridged the gap between theory and practice. He did not teach by rote memorization of diagrams, but by showing how systems failed in real life and how instinct, patience, and resourcefulness could turn failure into function. On the wall of his workshop hung a small, unremarkable artifact, a bronze bushing salvaged from the wreck of the SS Seminole, the same piece that had kept a destroyer's turbine alive in the middle of the Pacific. Its surface was still pitted from seawater and streaked with oil stains that had never fully faded. Beneath it was a simple plaque engraved with the words, "It is not what you work with that matters, but what you work for." For Miller, it was not a symbol of heroism, but of responsibility, the idea that engineering was an act of service, a commitment to the lives that depended on one's precision and resolve. His students remembered him as a quiet instructor who valued observation over talk. He would often take apart an engine component and pass it around the class, asking what each man saw, heard, or felt when touching the metal. He believed that true understanding came not from books but from the connection between the mechanic and the machine. Under his guidance, many young sailors learned that maintenance was not just a technical duty but a moral one, that a well-repaired engine was a form of protection for every man aboard a ship. The Navy's post-war training programs absorbed this philosophy deeply. The lessons from the Pacific War shaped the standard curricula at Norfolk, San Diego, and Great Lakes. Courses once focused solely on factory procedures now included modules on emergency fabrication, damage control, and resource management in isolated environments. Miller contributed to several of these revisions, helping to draft new sections on turbine repair and field lubrication systems based on first-hand experience. His reports and annotations became reference material for naval technicians throughout the late 1940s and early 1950s. Beyond the Navy, the influence of wartime field engineering extended into the civilian sector. Many former naval mechanics took jobs in shipyards, power plants, and manufacturing firms, bringing with them a mindset forged in crisis, the belief that systems could be adapted, redesigned, and saved even under impossible circumstances. The same philosophy guided the rebuilding of merchant fleets and commercial infrastructure that had been devastated by years of global conflict. Engineers who had once welded hull plates in tropical heat now taught apprentices in peacetime shipyards how to think independently and solve problems with limited resources. As for Miller, he remained in Norfolk for the rest of his career. In the 1950s he became a senior instructor and later an advisor to the Navy's Bureau of Ships, reviewing training materials for new propulsion systems. Though technology advanced rapidly, turbines grew larger, electronics replaced manual gauges, the essence of his lessons never changed. He reminded young sailors that no machine, however advanced, could endure without human understanding and care. When he retired, the small bronze bushing still hung in his classroom, darkened by time but untouched by replacement. The story of John Miller was, in essence, a story about the limits of endurance and the quiet triumph of will over circumstance. In a war defined by destruction, his act was one of creation. It was not dramatic in the way of battles or victories, yet it carried the same weight. On that drifting destroyer, surrounded by the wreckage of other ships and the immensity of the Pacific, he had confronted a truth older than technology itself, that machines are only as alive as the hands that tend to them. What he accomplished was less about the repair of a turbine than about the preservation of order in a world sliding toward chaos. The Second World War had revealed both the destructive genius of humankind and its capacity for resilience. Entire cities had been erased by fire, fleets shattered, and yet everywhere, men like Miller worked quietly to rebuild the very tools that allowed life to continue. For every bomb dropped, there was a welder sealing a hull, a mechanic restoring power, an engineer rebuilding a bridge. Their work did not make headlines, but it formed the connective tissue of victory. Without their persistence, the great engines of war, ships, convoys, supply lines, would have ground to a halt. Miller's repair was one thread in that vast network of endurance, an affirmation that progress is measured not only in destruction but in the stubborn refusal to yield to it. In the dim light of the destroyer's engine room, surrounded by noise, heat, and exhaustion, Miller's struggle reflected something universal. The tools he used were crude, the materials corroded, but the act itself was pure, an expression of purpose in the face of futility. He did not invent a new technology or design a new weapon, he simply refused to accept failure as final. That refusal, repeated countless times by engineers, sailors, and mechanics across the world, defined an entire generation. They were builders in an age of ruin, custodians of a fragile equilibrium between creation and destruction. The sound of the turbine coming back to life on that night was more than the hum of metal. It was the sound of human persistence echoing against the silence of the sea. Every rotation of that shaft was a statement of defiance. That ingenuity could still prevail even when the world around seemed intent on collapse. The ship's movement through the water symbolized more than propulsion. It was a testament to the idea that progress often begins not in laboratories or factories, but in moments of necessity, when thought and action merge under pressure. In Miller's work lay the essence of wartime engineering, the transformation of scarcity into possibility. The men who kept the ships alive did not see themselves as heroes. They were problem solvers, craftsmen, men bound by duty and the quiet pride of competence. Yet, in their uncelebrated labor, they preserved the foundation upon which victory was built. The history of the war often spoke of generals and admirals, but beneath every triumph was a mechanic tightening a bolt, a diver raising a part from the sea, or a machinist shaping a piece of metal to fit a broken machine. Miller's story stood for all of them. When he returned home after the war, the world he helped sustain had changed forever. The machines he once coaxed back to life had become symbols of a new age, faster, larger, and more complex. Yet the lesson he embodied remained timeless, that the soul of engineering lies not in perfection, but in persistence. Every generation that followed inherited that principle, whether repairing a ship, building a bridge, or restoring power after disaster. Technology, Miller had proven, was not separate from humanity. It was an extension of its endurance, its need to rebuild, its will to continue. In the grand arc of history, his repair might have seemed a small act, lost amid the enormity of the war. But the truth of it endured. It reminded those who came after that even in the darkest moments, creation was a form of resistance. Miller's hands, blackened with oil and salt, had held more than tools. They had held the idea that survival is a kind of art, and that to restore what is broken is one of humanity's deepest acts of courage.